Here we're looking at evaluating scalar line integrals in space, and specifically this problem is saying to convert our line integral to an ordinary integral with respect to the parameter and evaluate it. So first we want to remember our theorem for scalar line intervals. We have C f of x, y, z ds is equal to the interval from a to b. Now doing our function, can write it this way, f of r t, and then take that times the first derivative of that equation, the helix. So looking at these values, let me get a different color. Our c value here is what our curve is, and the s is the line that's going on that curve. Now in transitioning that over, we're going to recognize this part here and that part there as being our arc length. And the other way of writing this is to say this is the function using xt, yt, zt, with each of these then being the xt, yt, and zt. Okay, now in working on this, the first thing we want to work on here is getting pieced together the arc length there. So with that, we're going to need r prime of t. And plugging in our values here, we're looking at this, this is now becoming, take the derivative of 3 cosine of t, that becomes negative 3 sine t, and then 3 sine t becomes 3 cosine t, the derivative t just becomes 1. So then the next thing we need to do is take the magnitude of that, where we take the sum of the squares. So we're doing the square root is now going to be 9 sine squared t plus 9 cosine squared t plus 1 squared is 1. So we remember now this as being our trig identity for 1. So we just have 9 factors out of that. It becomes the square root of 10. Okay, so we have this that we can fit together here. So let's build our integral. We can solve for it. Root 10. Now let me give us a little bit more room. Taking the square root of 10, we'll just go ahead and move that out front for that part. Now the integral is going from a to b, and those a to b values that I forgot to write down up here, that is our value of, let's see, that was t is between 0 and 2 pi. That's very helpful to know that, from 0 to 2 pi. Okay, now what we do at this point is we're evaluating the function using our values over here. So for the y, we use our y over here, which is 3 sine t. And then it's going to be minus the z value, which is just t. And now we can put on here, this is going to be dt. Now let's take the integral. We have root 10. Now we'll let me split this up. We'll take the negative, the integral negative 3 cosine t that we're evaluating from 0 to 2 pi minus 1/2, taking the integral there, of t squared over 1/2. And then this is also from 0 to 2 pi. Now we plug in our values here, and we have, let me bring it over here, square root of 10. We've got negative 3. Treat that as a constant for both. It's going to be cosine of 2 pi minus the cosine of 0, and then minus 1/2, and then t squared. It becomes 4 pi squared, right? And then it would be minus 0. So that evaluates there. Now, of course, looking at this, the cosine of 2 pi and the cosine of 0 are the same value. So that just becomes 0. So in our final value here, we have a negative 4 times 1/2, 2. We still have our pi squared. And don't forget the square root of 10. So that gives us our answer.